In this video, we're going to be talking about van der Waals interactions. They're also called fleeting dipole-dipole, London dispersion forces. There's multiple names for this type of interaction. Basically, what this helps to explain is how come molecules that don't have any permanent dipoles are actually able to stick together at all, because we saw that the dipoles attract each other in that previous video, and that's how that helps the molecules to stick together. But if you don't have any polar covalent bonds in your molecule, you just have maybe carbons and hydrogens, so alkanes, for example, how are they going to stick to one another? How come we can see alkanes as liquids at all? Because we wouldn't expect there to be very much interaction between the molecules if we don't have any dipoles. This can be explained by our van der Waals interaction. So these are what happens when molecules kind of get close to each other. These dipoles can actually be induced on the molecule, and that's from electron repulsion. So we're going to take a look at just a general molecule A and interacting with molecule B. And molecule B is just maybe another molecule of whatever substance we're dealing with. And so what's going to happen as these molecules kind of start to come together is that, say there's just randomly, this is also caused by random electron movement. So randomly, there just happens to be a little bit more negative charge on the bottom part of A. As it's starting to come towards B, what that's going to do to the negative charge on the top part of B is it's actually going to cause those to go to the opposite side of the molecule. So that's going to, through electron repulsion, start to shift to the opposite side of the molecule. So what that's going to do is it's going to start to leave a little bit of a positive charge at the top. Then the negative is going to be on the bottom of that molecule. Another molecule comes along, and so say molecule C comes along, what's going to happen is B is going to do to C what A did to B. So that same thing's going to happen, and they're basically all going to start to stick together because of those random electron movements that randomly kind of made A have more negative charge on the bottom of it, and that kind of caused those movements in B, which is going to cause movements in other molecules. And so these are going to start to be able to stick together because of this electrostatic attraction between the negative and positive charges on the two different molecules. The strength of these dipoles does depend on the contact area between the molecules. So we have small molecules versus large molecules. Small ones don't have as much contact area in between because there's not as much surface area that can actually interact. And so we don't have as much contact in small molecules as we do in large. So in large, we could have the same type of interaction over that larger surface. And so it's going to be, since this is an additive type interaction, we're going to end up having a stronger interaction for the large molecules. What that stronger interaction is going to mean is that we're going to have a higher melting point or boiling point compared to the small molecule. So generally larger alkanes, for example, will have higher melting points or boiling points than smaller alkanes. We can also talk about linear and branched molecules. So if we have a linear molecule, we basically have that carbon, the zigzag of that carbon backbone pretty much being, it's still zigzag, so it's not a completely a line, but it's all kind of in that same zigzag and in one direction kind of thing. With branch, this is where we have alkyl groups coming off of maybe that main carbon chain, and what we find with branch is that we actually have less contact area because the other groups are kind of getting in the way. So we have less contact area here in the branched than we do in the linear. So what that's going to mean for the linear molecules is that they're going to have the stronger interactions because they have more surface area that can contact, and that means we're going to have a higher melting point or boiling point for linear molecules versus branched. Let's take a look at what that means in terms of real molecules, not little bubbles anymore. So with this one, which of the following two compounds will have the highest boiling point and why? So we kind of have two of them there. What we see is that they're alkanes, so we don't see any dipoles in the molecules at all. So we're taking a look at what's the difference. The difference is this one is a nice linear zigzag. This one is an example of where we have some branching coming off of the chain. And so these molecules aren't going to have as much contact area as something like this. So we're going to have more contact area for this one on the left because it's linear. And we're going to have a stronger van der Waals interaction. What that's going to mean is that basically the molecules are going to stick together better. And that's going to mean we're going to have the higher boiling point. That's what the question's asking about, boiling point. So typically these types of questions are about four or 5 points for this, because you do have to mention that what is the main difference, so that more contact area, stronger interaction is important to mention, and the type of interaction. So we're dealing with van der Waals here. We've seen dipole. We're going to see one more after this. So that's kind of why I wrote the van der Waals in, just because you do have to identify the type of interaction. And then saying that the molecules stick together better. So kind of like why do we see this higher boiling point, and then kind of identifying the fact that that does have the higher boiling point. So then we have this question down here where we have same kind of the same molecule actually there, but this time we're comparing it to propane. And so what we see with this one is if we have, now it's not so much linear versus branch because they're both more or less linear, we have a large versus small molecule. And so we said with larger molecules, we also have the higher contact area. So this one is still going to be our higher boiling point. And for those same reasons, so more contact, this time because it's larger than the other molecule we're comparing it to, so stronger van der Waals interaction, which means the molecules will stick together better. And it's harder to separate them. So this one's going to have the higher boiling point. So that's what happens when we don't have any permanent dipoles, but so we're usually going to be using van der Waals interactions when we're talking about alkanes or alkyl groups. We're going to be dealing with van der Waals between like alkyl chains, or just for alkanes themselves that just have carbons and hydrogens in them.